Here's a situation where someone lifts a 0.5 kilogram ball from the floor all the way up to a height of 2 meters and holds the ball there. Now, in that position, the ball has what we call gravitational potential energy. In fact, we can work it out. It's quite an easy formula. Gravitational potential energy, EP, is equal to the mass of the ball times the gravitational field strength of the planet multiplied by the height that you lifted the ball to. EP equals mgh, and we can work it out as follows. EP, the gravitational potential energy, is equal to the mass of the ball, 0.5 kilograms, multiplied by G, the gravitational field strength, 9.8, and newtons per kilogram is units for that, multiplied by the height which the ball was raised to is going to be 2 meters. If we do that on a calculator, we get an answer of 9.8. Now, let's think about the units. We have kilograms cancelling with kilograms, and we're left with a Newton metre. But that's an old friend, because Newton metre is units for work done. Remember, work done is energy transferred. So what we've done, if you pardon the pun, is we have transferred 9.8 joules of energy to give the ball gravitational potential energy. Remember, the word potential means the ability to do something. So that ball in this position has the ability to either stay there if you hold it, if you let it go, it will fall back down again. Its gravitational potential energy will have changed into kinetic energy. So at this position here, we have the gravitational potential energy of the ball equal to 9.8 joules. Now, let's see what happens when the ball falls down here, because this is the whole key of conservation of energy. If we think of a kind of bar graph, what's happening in this position here, the ball has all got potential energy, gravitational potential energy. It's held steady, there's no kinetic energy. When you let the ball fall all the way down to the bottom, just before it strikes the bottom, all the gravitational potential energy has been changed into kinetic energy. You have this transfer of energy. Now, conservation of energy means that if there's no friction involved, no air friction or no loss of energy with the sound, the kinetic energy the ball will have at the bottom of its journey will be exactly equal to the potential energy it has at the top of its journey. What happens midway? Well, midway we're going to get a split in the energies. You can see that we're going to have half kinetic and half potential energy. Now we put numbers into that. We know that at the top of the 2 meters, the gravitational potential energy has got to be 9.8 joules. At the bottom, that gravitational potential energy will be changed completely into kinetic energy, but will have the same value, 9.8 joules. Halfway down, you're going to get half the energies. So half of the gravitational potential energy will have been changed into kinetic energy. So you're going to have only 4.9 joules of gravitational potential energy left, and that's been changed into 4.9 joules of kinetic energy. And that's what we call the situation when it's halfway down its fall. So conservation of energy really amounts to this. When you lift the ball up to a certain height to give it a certain amount of gravitational potential energy, in this case 9.8 joules, and you allow the ball to fall back down again, then all its gravitational potential energy will be changed into kinetic energy, and both will be equal. So we can say that the gravitational potential energy here is changed into kinetic energy down at the bottom. And likewise, vice versa. If we start off the ball with kinetic energy at the bottom, as give it a launch, then that kinetic energy will be changed into gravitational potential energy at the top. So really these two things are the same. We know that the gravitational potential energy is going to equal to the kinetic energy at the bottom. And this helps us solve quite a lot of really useful physics problems, knowing this idea of conservation of energy. Let's take a look at the algebra of that situation. Here we have a person who is lifting a mass of m kilograms through a certain height h. Now we know at this position the ball, or the mass of the object, whatever it is, will have gravitational potential energy equal to mgh. If the ball is allowed to fall back down to the ground, then just before it strikes the ground, all that gravitational potential energy will be changed into kinetic energy. So both of these expressions should be equal. So we should have this situation here. We should have the gravitational potential energy equal to the kinetic energy at the bottom. Both are equal. Now we can use that expression to solve all sorts of problems, as I've said, by just equating the two expressions. So if we have, for example, EK equal to EP, so the kinetic energy will be equal to the gravitational potential energy, and we put in our values of these, a half mv squared is what the kinetic energy is, that should equal to mgh. Now that looks a complicated expression, but it's not that hard. If you look at both sides of it, you can see mass appears on both sides. So what I can do is I can actually rub out the mass on both sides, they cancel out. And I'm left with a very strange looking equation of 1/2 v squared is going to equal to gh. Now when you look at that, you can find then the height the ball rose to if you know its launching velocity, and you can know the speed of the ball as it strikes the ground if you know the height it's dropped from. And that's what we'll be doing in our next couple of problems. We'll be using conservation of energy to solve problems like that, and we always end up with this little equation here, which doesn't contain mass. Okay, let's try and work out the speed of the ball as it strikes the ground using our conservation of energies. The mass of the ball we'll take to be 0.5 kilograms. And the height which the ball was lifted up to was 2.0 meters. And our job is to find the speed of the ball as it strikes the ground. So what we have to do is look at the energies of the situation. So at the top, the energy of the ball will be completely gravitational potential energy of the value mgh. At the bottom, all that gravitational potential energy has been changed into kinetic energy, half mv squared. And both of those values should be in fact the same. So those values are the same. EP should be completely transferred into EK. So remember, we have to find the speed of the ball at the bottom. So let's work it out in terms of algebra and put our numbers in. So EP we know is equal to EK, so we can also say that EK is equal to EP. I'm choosing EK first because EK has got the V in it. So we keep that in the left hand side, 1/2 mv squared is going to equal to mgh. And you can see that mass can cancel from both sides. So mass here and mass here can cancel. So really we don't really need to know the mass of the ball. We can actually do even a calculation without knowing the mass of this ball. We can calculate speed. It only depends on the height in which it was dropped from. So we have 1/2 v squared is going to equal gh. So if we multiply by 2 all the way through, we have v squared is going to equal to 2 times g times h. And therefore, to take v on its own, it will be the square root of 2 times the gravitational field strength times the height the ball is above the ground. So we can put in our numbers now. We know it's going to be the square root of 2 multiplied by 9.8 times the height of the ball is going to be 2. And we can actually take the square root of that, get our answer in a calculator, and we end up with an answer of 6.3, and it'll be meters per second. So we've now found out the speed of the ball just by knowing the height the ball was dropped from. Let's use our conservation of energy theory again to work out the height a ball reaches when it's launched with a certain speed. So in this diagram here, we've got a special contraption which is going to ping the ball into the air, and it tells us what the speed is when it's leaving the pinger. So it's leaving the pinger with a speed of 9.0 meters per second. It's got a mass of 2 kilograms. So what height will it rise to? That's our key question here. Now we know that when it leaves the launch device, it's going to have an initial kinetic energy of a half mv squared. Once on its way up to the very top, then that ball gets to the top here. All its kinetic energy will be transformed into potential energy, EP equals mgh, and we want to find what h is. So we start off equating as follows. We start with EP because that's got the h on the proper side, so we start with EP here, and that's going to equal to EK. We know EP equals mgh, and that's going to equal to 1/2 mv squared. And you can see that mass does not come into it. Mass will cancel from both sides, like that. So we're left with GH, gravitational field strength, times the height, is going to equal to 1/2 v squared, the launch speed. So divide by g and we're left with what height is. It's 1/2 times the speed squared divided by g. Don't worry, just plug the numbers in now. We've got 1/2 times the speed squared. 9 squared is 81, so it's a half of 81. I'll put a wee bracket in that to keep it tidy. Divided by 9.8. Now if you do that in your calculator, you'll get the value, the height the ball rose to is just about 4.1 meters. Now these are complicated problems, but more practice using our conservation of energy, we can work out the height a ball went to, and we can work out the speed that a ball landed to just by equating our mgh and our half mv squared and cancelling out the masses and rearranging both sides. A question before we finish this lesson then. What height would another ball launched with the same launch speed of 9.8 meters per second reach if that ball was in fact not 2 kilograms but this time 10 kilograms? So a 10 kilogram ball launched with the same launch speed, what height would that rise to? Think about it.
Physics is wonderful. Physics is cool.